Hi guys, so today we'll be going into corner detection using OpenCV. So this is the workflow. First I'll be talking about what are features, just a basic overview. Then we'll dive deeper into corners, what are corners, their applications, how to do corners, etc. Here, understanding features. What are features? So when you have multiple frames of a particular environment, the most significant points of in that environment are known as features. This most significant points are usually taken by detecting the matching points in all these frames. So here, the matching points between all frames of an environment are defined as the characteristics of that environment. So these characteristics are known as the features of the environment. So these features are used for recognition of the environment. Suppose at a later time, if you want to detect or recognize the environment, then your computer model will look for these features, these characteristics in the environment, and if it's able to detect these features, then it will recognize the environment and give it the name. So unless they're uniquely recognizable, you can't call them characteristic features, right? So they will always be uniquely recognizable. So every environment has different features. So there are three main types of features that we look at: edges, corners, and blobs. So we'll be diving deeper into corners. So here I've mentioned them to be points of interest. So what are corners? Corners are basically nothing. They are the meeting point of edges. So wherever edges meet, those are known as corners, like in basic maths. So there's a different definition here. We can also recognize corners when there is a large variation in pixel values. So wherever there's a large variation in pixel values in all directions, those are also known as corners. So it is the intersection of two edges, right? So why do we do corner detection? Feature extraction. So feature extraction is a very important step when you build models that detect and recognize stuff. Like suppose you want to build a deep learning model that classifies road signs, or a CNN model that looks at people and determines whether they're wearing a mask or not. So for all these kinds of applications, you need the basic step is feature extraction. So corner detection is a part of feature extraction. You need to extract these corners to be able to understand the characteristics of the image and for the model to be able to later recognize these in a whole new environment. So when there is new data being given to the model, once it's deployed, it looks for these features, and then if these features are found, then it will detect whether the person's wearing a mask or not, whether this road sign says 30 kilometers per hour or 70 kilometers per hour. So it's all dependent on these three main features. So like I've mentioned, the applications: motion object tracking. So when there's a moving object and if you have to track that, for example, in automated vehicles and stuff like that, where you have to track moving objects to follow them. So corner detection is used over there. Then it is used in 3D modeling. And this example I've taken here right now, like recognition of road signs or determining whether a person is wearing a mask or not. These all come under detecting and recognizing objects and shapes and other things. So in all these cases, corner detection, feature extraction play a major role. Now, how to perform corner detection? There are two mostly used techniques: Harris corner detection and Sheath-Homasi corner detection. There's not much difference between the two. This is just an improved version of the first one. So we'll move on to the first technique, the Harris corner detection technique. It was formulated in 1988 by these two people, Chris Harris and Mike Stevens, came up with a mathematical formula to identify this, a large variation in pixel intensity in all directions. So they gave a mathematical formula to be able to do this. So using our mathematical formula, this function uses this mathematical formula to identify corners. Now how they came up with this formula and how this helps in corner detection, I won't be going into the details, so I have mentioned a few references here. This is a website and this is a video, so you can go through them to understand how this formula works and how they came up with it. Now, like I've mentioned, OpenCV has a predefined function which uses that formula to detect corners, cv2.corner-harris function. So here I've mentioned the parameters that it takes, and there are some constraints. So I have mentioned their data types and the case size. It should be odd, and the odd number should not be greater than 31. So that's something you should keep in mind. The rest are, I've just mentioned the data types, so that's all right. Now we'll go into the code. So as usual, we'll load our image first, then we'll convert it to grayscale. So this algorithm, it works only on grayscale. This function, it works on grayscale images. So you have to first grayscale it. Now once grayscale is done, you have to convert it to a float image. So I've mentioned here the input image should be grayscale and float 32 types. So that's what we'll be doing here. So once that's done, we'll use the cv2.corner-harris function. We'll pass the gray image and we'll give these parameters that I've mentioned here. And then we'll move on to using the function on our grayscale image. Along with the grayscale image, you have to pass these parameters, values of these parameters. Once that's done, we'll dilate the image to get a more clear picture of the corners, and we'll specify a threshold value. So threshold value is basically to give you the more significant corners. So if a corner is greater than the threshold value, only then will it be considered as a significant corner and will be displayed on your final image. Suppose it doesn't match the condition, then it won't be considered a significant corner and hence won't be displayed on your final image. So that's what we use the threshold value here for, so that we get an optimal value for the corners. So we'll do that. What we're doing here is we're taking the detected corners, applying the condition of threshold to them, and then we'll be multiplying with the maximum value, and we'll be replacing this, what we get here, the pixel, with a colored pixel so that we can mark the corner. So we're basically replacing the pixel value where the corners appear with the pixel value of a color, so that we'll be able to see the corners in our image. Now once that's done, we'll display the final image along with their corners. Now we'll move on to the next technique. So like I've mentioned, this is a modified version of the corner detection method. It's just an improvised version. So in 1994, these two people made an improvisation to the previous one, and this is mostly used more than the Harris detection technique because it shows better results. So how this works and what is the modification made are all mentioned in these two. Again, this is the website and this is a video, so you can go through them to understand what the mathematics behind the formula and the modification is. So this is the inbuilt function in OpenCV, which helps to detect corners. Using this function, you can use the Sheetomacy technique or the Harris corner technique. You can mention it actually as a parameter when you're passing the function. So it can detect, using both techniques, So sheet-omc doesn't have its own function. We normally use good features to track function to detect corners using the sheet-omc technique. So as I mentioned here, this function finds n strongest corners. So what this function does is it takes corners, it first detects corners using the Harris corner detection, then it places them in a descending order, and it picks the n strongest orders from that list. So suppose you pass a value of 25 as n, then you will only get 25 corners in your final image. So if you say you pass 100, then you will get 100 corners that it has detected in the final image. Again, I have mentioned the parameters it takes and the data types. So this minimum Euclidean distance between corners is another added modification. So workflow. So like I said, it finds all the corners using the Harris corner detection technique. Then it will reject corners below this quality level. So here there's a quality level parameter that we pass, and it's a float. It's always between 0 and 1. So if your corners values are below the quality level, then it rejects those. After it rejects those, as I mentioned earlier, it sorts them in a descending order based on their quality. So once it sorts them, it picks the strongest one. So in that order, it picks n strongest ones. So this part will be repeated n times. So it picks the strongest corner and it discards all the corners that fall in the range of the minimum Euclidean distance. So anything that is closer to the corner that it picked first, it will reject all those and it will move on to the next one. Once this step is done for n times, it will return all the remaining corners. Whatever is left, it will return those as the actual corners of the image. So all of this is done using one simple function. So that's the good thing about OpenCV. As usual, we'll load the image first, then we'll convert it to grayscale. It works only on grayscale, so you have to convert it to grayscale. Here I've mentioned it. So we'll convert it to grayscale, then we'll use the cv2.good features to track. We'll pass the image, the gray image. Then we'll set. So this is the number of corners we would want to detect. So I want to detect 100 corners in my image, so I passed 100. And this is your quality level here, as I've mentioned, and this is the Euclidean distance. So suppose the algorithm, it detected two, 3 corners in a distance of 10. So it picks the strongest corner out of those and it discards the rest. So there will be no corner that is within 10 units of the strongest corner. So after that, we'll convert it into into a numpy array of int, and then we will plot circles at each of these corners. This is the color specification, this is the radius, and this is the center point. So we'll use cv2.circle to plot these points. Once plotting is done, we can display the image. Now we'll see how it works. So this is the image I've used. So we'll see how Harris corner detection works. So this is the original image. We'll be displaying the original image first, and then this is the corners detected image. So as you can see, it has detected all our corners perfectly. So this depends on the values you pass. So it keeps changing for each image. You can't give the same values for every image. So you have to do trial and error to get the right values for your image. So this I've just shown the output here. Then sheet geometry technique. So this is the original image, and this is the corner detected image. So the same as before, but it's just better improvised technique. So most people tend to use this technique. And this is the output just to show you. Now I want to mention one thing here. So in this case, what we're doing is we're replacing the pixel values, right? So this point is actually embedded in the image. So the original image, this color is replaced with red. Same with all the points. This color is replaced with red. So here we'll be replacing the pixel values. But here what we're doing is we're drawing a circle over the pixel. We're not replacing the pixels, but we're drawing a circle. So here, as you see, this is a circle drawn over the pixel. So we're not replacing here. Again, we're drawing it over the image. So there won't be any change in the original image. But here, if you see, there will be a change in the original image. So that's it, guys. Thank you.